Hi, my name is Martin Avanzini, and in this short video I give you an overview of our work in modular cost analysis for probabilistic programs. This joint work with Georg Moser and Schaper. So the main contribution that you will see today is a novel way to derive symbolic bounds on the resource usage of probabilistic programs. Such a static resource analysis is a well-established research field where various techniques have been introduced. However, a majority of these techniques are confined to sequential models of computation. If you look at application areas such as cryptography of robotics, the underlying model of computation is inherently randomized. This motivates us to look at probabilistic programs, so ordinary programs, that have in addition some source of randomness built in. From an operational perspective, computation should then really be conceived as stochastic processes. Orthogonally, if we look at resource analysis, it's very natural to assign a cost to your basic operations and then define the cost of the computation as the accumulated cost of all the operations that have been performed. In a sequential setting, we would now be interested in giving a symbolic upper bound to the so-defined cost. In a probabilistic setting where costs can differ between different probabilistic execution branches, the so-defined cost is in fact a random variable, and here we will be interested in binding its mean value. So to make this more concrete, let's look at this simple implementation of a biased random walk. In each loop iteration, we flip a coin, and depending on this coin flip, we either increment or decrement the variable x. Now in this last statement, we indicate that each loop iteration consumes one resource unit. So the cost is given by the number of loop iterations. While this example is potentially non-terminating, the expected cost is finite. However, if you want to derive such a bound by hand, this is very often difficult and it's always tedious and error-prone. This is precisely the problem that we would like to overcome. Concerning the state of the art, all these techniques are related to what I call here probabilistic ranking functions. Such a probabilistic ranking function assigns to your program states a positive number, the so-called rank, that should decrease in expectation by the cost of operations that you're performing. If you have such a function, then this function indeed gives you an upper bound to the overall program cost, and in fact this is not only a sound but also a complete methodology. It suggests the following two-stage approach. We take our program and we extract from this program a set of conditions that describe this ranking function condition, and then in the second stage we apply a dedicated constraint solver that synthesizes a concrete ranking function. While the first stage, at least from a computational perspective, is relatively easy, the second stage is computationally very difficult. The problem underlying this approach is that it's a whole program analysis, so we cannot expect it to scale well to more interesting bigger examples. So what we would really like to have is a more modular kind of analysis where we analyze different program fragments independently and then have some means to combine these intermediate results to an overall bound. This is precisely our first contribution. It's based on the ERT Calculus of Kaminsky, and to achieve modularity and thus scalability of the analysis, we interleave it with value analysis. We have proven this methodology sound with respect to a novel operational semantics that we have defined, and we also provide a fully automated implementation that is competitive in strength, but due to its modular nature, often orders of magnitude faster. The language that we are considering is a probabilistic variation of Dijkstra's guarded command language, where additionally we allow sampling from integer valued distributions, and we have this consume statement to incur a cost of computations. Some notions that we should fix. First of all, program semantics speak about stores, so integer assignment to your program variables. Since the program is probabilistic, the outcome will be a distribution over such final states. The expected cost function of a given program C maps initial stores to the expected cost of running this program, and the expected value function computes the expectation of a given function on the distribution of final stores that we are obtaining, measured in terms of the initial store. As I mentioned before, we base our work on the ERT calculus, which is itself a generalization of the weakest precondition calculus of Dijkstra. This calculus essentially defines the so-called expected resource transformer that takes a function which explains the resources that we would like to have available after executing, and it transforms it into a resource requirement that we have before executing the given program C. Now, of course, this transformer generalizes seamlessly from a transformer to reason about expected runtimes to one for reasoning about expected costs. The details you find in the paper. The first thing I would like to point out here is that this expected cost transformer now gives us a mean to, on the one hand, reason about the expected cost of a program, and on the other hand also reason about the expected value of functions with respect to programs. From a different perspective, this allows us now some form of horizontal reasoning for reasoning about these two quantities. Here the challenge, of course, is to deal with while loops, and to that end, quite similar to the case of Dijkstra's predicate transformers, we employ invariants. More precisely, so-called upper invariants. So an upper invariant itself is a cost function which will, by the following two conditions, give you an upper bound on the expected cost of running such a while loop. This condition morally states that whenever the loop guard holds, so whenever we iterate the loop command, this invariant should on the one hand account for the cost of executing your loop's body C once, plus the expectation of the invariant after executing the command C. And it should be non-negative whenever we exit the loop. So now we can actually use this upper invariant result to go back to our two-stage approach of constraint extraction and constraint solving. Let's illustrate this one on the biased random walk. In the first phase, the constraints that we would like to extract explain this upper invariant condition. To this end, we first represent the invariant, which will give a bound to the cost of this while program symbolically. Our symbolic representation consists of a linear combination of so-called base functions. These base functions are simply abstractions of your program stores as non-negative numbers. These base functions itself are obtained by inspecting the programs before we proceed with the constraint formulation. Now let's suppose, for the sake of simplicity, that our algorithm for extracting suitable base function simply decides that we would like to abstract our program store by the absolute value of the program variable x. In this case, the invariant has simply the form a coefficient k to be determined times this abstraction. So we can now go and substitute this invariant in these two upper invariant conditions. So what you now see here is that it makes reference to the expected cost and the expected value function with respect to the loop's body. Since these two functions are itself characterized by the expected cost transformer, we can now reiterate and recurse this methodology and substitute or pre-compute these two quantities and substitute it within this constraint. Now in this example it's quite simple because the loop's body is a simple straight line program, and we obtain the following two constraints that are drawn here. The only unknown quantity now is the coefficient k that we now wish to synthesize. To this end, we first reformulate this constraint as a non-negativity constraint, upon which we can then use a positive Stellensatz such as Handelmann's theorem to extract the SMT formula. On this SMT formula we apply an off-the-shelf SMT solver whose solution, in this case k equal 2, can now then be substituted back into our template, thereby deriving the bound 2 times the value of x for this concrete example. So this gave you a very informal and brief overview of our methodology. I would like to conclude with an experimental evaluation. To this end, we have implemented this approach in our tool EcoImp and compared it to the Absinthe prototype of NGO et al. And the prototype of Wang for reasoning about expected costs of such probabilistic programs. We compared it also to C4B on a set of non-probabilistic programs. As test bench, we essentially used the benchmarks underlying these tools plus a handful of new examples from our paper. In conclusion, our tool is comparably in precision and strength on the probabilistic and the deterministic benchmarks. More advanced examples that we will see in a moment can only be solved by our new implementation, but the big benefit is the speed up that we obtain, where on average our tool performs 2 orders of magnitude faster. So here are some representative examples. The first example is the running example on the paper that introduces the Absinthe prototype. This is the trader example. This example essentially models the behavior of a stocks trader. The stock price itself of a share is modeled by a biased random walk. Whenever the price changes and is above a minimum price, the trader decides to buy between 0 and 10 shares. The expected cost of this program models the expected amount of dollars that the trader is supposed to pay on these shares. So what you are seeing here is that the inferred bound, this actually holds for all the 3 tools that are drawn here, is very close to the actual measured cost of this program. However, in comparison, you also see a major increase in execution times, which is due to the modular nature of our tool. The second example is a running example of the paper that explains the ERT Calculus. This example models the coupons collectors problem. So very briefly, in the coupon collectors problem, we ask ourselves, if we have a big pot of coupons and different coupons, how many draws do we have to make on average to collect all n coupons? The expected cost of this program actually models now the expected number of draws that we have to perform. While a manual analysis can derive the optimal bound n times log n, such an analysis is very involved and takes up several pages. On the other hand, we can derive with our tool again a quadratic bound within a fraction of a second. Last but not least, to look at the scalability of our approach, we also benchmark the tools on a series of examples. The program nest_n essentially performs n nested loops, and here we see that in comparison to other tools where the performance is sharply degrading if we increase the nested of loops, within EcoImp the performance remains relatively stable, measured in terms of the number of nested loops. So this brings me to a conclusion. What you've seen today is a novel expected cost analysis for probabilistic imperative programs, whose main benefit is its modularity and therefore scalability. It's proven sound in terms of a novel operational semantics that you can find within our paper, and we have also provided a fully automated implementation that is freely available. Thank you very much. If you have any questions, I'm very happy to answer them in the dedicated question and answer session.